So please, Nikola, you can make your presentation. And thank you very much for accepting our invitation. And you have 30 minutes, okay?
Okay, I'll prepare 20 minutes, but I doubt that anyone will
ask some questions.
Okay. So hi everyone. I'm Nikola Adžaga from Zagreb, Croatia. I would like to thank the organizers for giving me the opportunity to give a talk at this conference with such an interesting topic, especially after such an amazing lecture we had before this break. So what I would like to talk about is automated conjecturing of Frobenius numbers by grammatical evolution. And I will start by saying a few sentences about each of these terms in the title. So unlike automated theorem proving, which can be considered like a specific subfield of mathematics, I think that I would not consider automated conjecturing as a well-established subfield of mathematics. It is something that has been done mostly sporadically. And I would like to mention some examples that I think that were somehow significant, and I don't think they have been mentioned on the conference before. So the first example is graffiti. So this was a computer program written by Feitlovich already in the 1980s. This program has generated hundreds of conjectures in graph theory and inspired, well, if not hundreds, then at least dozens of papers, including some by Erdős. And another one that wasn't maybe so significant in terms of results is the Colton's HR program, which generated some new results in number theory. For example, a necessary condition for a number to be perfect. But what I find most interesting is that this is the first time, at least I think this is the first time that someone has written down explicitly to consider mathematics a new domain for data mining. And this was more than 20 years ago. Okay, and what I would like to show in this talk is that grammatical evolution can be useful in mathematics. And the problem that I have chosen to show this is the Frobenius problem. Okay, so this problem asks for the following: given relatively prime positive integers a1, a2 up to an, now we can assume that they are ordered, so a1 is the smallest one. So the problem is to find the Frobenius number, which is the largest positive integer that is not representable as a linear combination of a1, a2 up to an, where the coefficients are non-negative integers. And we'll denote this Frobenius number by G. And we will say that the number is representable if it can be represented as such a combination. So for two numbers, it has long been known that their Frobenius number is their product minus their sum. This is usually attributed to Sylvester. So I believe this is clear, but maybe to make it like more interesting, so you can consider this Frobenius problem as a coin problem. So say that you have coins of different values, for example, of 3 and 4, then the question is, what is the largest value we cannot pay using these coins? So if you use coins of value 3 and 4, then the Frobenius number is 12 minus 7, so this is 5. So this is the largest value that we cannot pay using only these two types of coins. And now if we have 3 types of coins, the quest for a similar simple formula was not successful, although there have been a lot of attempts. And perhaps a bit surprisingly, Curtis has shown that this quest cannot succeed. To be more precise, what he has shown is that there is no finite set of polynomials such that for any triple, you can compute its Frobenius number by plugging it into one of these polynomials. Still, there are efficient algorithms for Frobenius number of 3 different numbers. For a fixed n that's greater than 3, so for 4 and above, there is a polynomial time algorithm, but it is impractical. So its complexity looks something like this. So already if you have n being 4, then this exponent will be 4 to the power of 4, and that is considered too slow. And on the other hand, there are formulas for Frobenius numbers of arithmetic sequences of arbitrary length and for geometric sequences of arbitrary length. And for quadruples, there is a lot of different formulas for Frobenius numbers. For example, this one is a fairly old one. So if these 4 numbers are very close, then it's not hard to find a formula for the Frobenius number. Okay, now I would like to say a bit about grammatical evolution and how do we use Frobenius problem on it. So to explain grammatical evolution, I need to say a bit about grammars. So this story started with Chomsky, who was looking for simple rules capable of describing English language. And he defined and found context-free grammars as sufficient for formalizing at least the syntax of English language. And to define these context-free grammars, I need a little bit of notation. So if we have an alphabet A, by A star, we'll denote all finite words that can be written using this alphabet, starting with an empty word, 1-letter words, 2-letter words, and so on. Then a context-free grammar can be defined as a quadruple, where the first element T is the set of terminal symbols. The second element N is the set of non-terminal symbols, so this N has to be disjoint with T. P is a finite set of production rules, allowing us to replace a non-terminal symbol by a word consisting of both terminal or non-terminal symbols. And finally, we have the start symbol. Okay, this may look strange, so I will give 2 examples. So the first example, let's say that the terminal symbols have only, so there are only 5 terminal symbols. So there is this A, maybe like a variable A, then there is this times, plus sign, and the brackets. The non-terminal symbol is only one, it's E, and it stands for an expression. And the production rules allow us to replace an expression with an expression plus expression, or an expression times expression, or to put this expression into the brackets, or to replace it with this letter A. And the start symbol is E. So when you look at it all together, it's not really clear how to use it. So usually it's not written in this form, it's written in a different form. So this is a second example of a context-free grammar. So here we only give the production rules and everything else is concluded from it. So these non-terminal symbols have brackets around them, while terminal symbols do not have brackets around them. And the start symbol is simply the first symbol that's written down. So this is the expression here. So the way we read this is very, very simple. So expression can be replaced by an expression operator expression, or the same thing in the brackets, or maybe by some pre-operator applied to an expression, or by a variable. Then operators are just these basic operations, while pre-operators can be, say, trigonometric functions or exponential logarithm. And similarly, let's say that variable can be either x, or maybe it can actually be a constant one. Okay, so I have said a little bit about grammar. Let me say a bit about evolutionary algorithms, although this is something you have probably heard of. So maybe the problem to have in mind is some kind of an optimization problem. So what evolutionary algorithm does, it initializes a whole population of potential solutions called individuals. These individuals are usually just some binary sequences or sequences of integers that are somehow mapped into the potential solution of our problem. Then this population is evaluated, which means that we somehow measure how good is each of these individuals at solving our problem. And then, as long as this some termination condition is not satisfied, we do the following things. We recombine our existing population. For example, we can use reproduction of the individuals. So if these are binary sequences, then the reproduction can simply be applying a logical operator and bitwise or something similar. Then we can also mutate our population, which means that we take some individuals and maybe alter some of its bits. And then after all these changes, we evaluate our new population and choose the best individuals for the next iteration of our population. And we continue doing this until we say find a solution, or until say 500 iterations pass. Okay, so now the question is, how do we combine these two things? How do we create a potential solution or a potential expression from a binary sequence or a sequence of integers? So here I will explain this using this example of grammar that I've already given before. So let's say that the first integer is 220 and the start symbol is, like we said, the expression. We look at the rules that we can use for the expression. Well, 220 is 0 modulo 4, so we use the rule that has this tag 0. So we replace expression by an expression operator expression, and now we focus on the first non-terminal symbol we have, which is again expression. The next integer is 240, again 0 modulo 4, so we again use the same rule and replace expression by expression operator expression. Now the next integer, 203, is actually 3 modulo 4, so we replace this expression by a variable. Now the next integer is 101, and we have to look at our rules for variable. We have only two options. 101 is odd, so we replace this variable by 1. And now we move on to the next non-terminal symbol, which is operator, and we use the next integer 53. For operator, we have 4 options. 53 is 1 modulo 4, so we replace this operator by minus. And so on. Once we run through this whole sequence of integers, what we end up is an expression looking like this. Okay, so now we know how to map a sequence of integers using our grammar into a particular expression. And the question is now how to use this, how to apply this on the Frobenius problem. Well, let me start with the input data for this grammatical evolution. So we have computed a Frobenius number for 40 quadruples of the shape x, x plus 3, 2x plus 1, and 2x plus 7. There's nothing really special about the shape of this quadruple. It was simply chosen as a simple form for which Frobenius number was not previously known. Okay, so now what do? We give this as the input data to our grammatical evolution, and particular individual solution is evaluated in the following way. So we get an expression like we had on the previous slide, and we evaluate it for our quadruples or for our x's, and we compare the value we get with the Frobenius number. The closer this value is to this Frobenius number, we will consider an individual better. Or to be more precise, the error value or the fitness value of a particular solution will be simply the sum of all the differences between the value our expression gives and the actual Frobenius number. And once I have run this for these 40 quadruples, okay, the grammar I have used is very similar to the one I have shown you before. There are some slight differences. For example, since I expected some larger constants to appear, I have given more freedom to how the constants behave. So this is given here at the end. And I will maybe say a few more words later about it. But for now, let me say that once I given these 40 quadruples, this input data into the grammatical evolution using the grammar on the previous slide, what it has found was an expression that had not that was not completely correct. So it had an error value which was not 0, but it had a very low error value. And once I looked at the specific quadruples and their error values, I realized that this formula was actually valid for every third quadruple. And it turns out that this formula is really valid for x being 3k plus 1 and k being at least 5. So we got the following conjecture: Frobenius number of a quadruple 3k plus 1, 3k plus 4, 6k plus 3, and 6k plus 9 for all k greater or equal to 5 is given by this expression given here. Okay, so you might be wondering, where does this floor function come from, since it did not appear in our grammar? Well, the reason why this floor function appears is because I have used C programming language, and the numbers we have used were integers. So C uses the integer division. So for example, 8 divided by 3 is 2 in C. So C discards this fractional part if these numbers are integers. Okay, and the second thing you might be wondering, I've said conjecture, and here I've written down the theorem, and yes, indeed, I managed to prove this. So the proof uses this lattice point enumeration method developed by this team mentioned here, and their mathematical package was crucial for proving it. So let me say just a few sentences about this proof method. So their method uses the geometric structure of a fundamental domain D having A1 or 3k plus 1 points in our cases. And this fundamental domain corresponds to a tiling of z to the power of 3 in our case, which is constructed from this quadruple by using all the elements except the smallest one, except the first one. And this domain encodes the information needed to find the Frobenius number. So by using their mathematical package, I realized that for these quadruples, this fundamental domain had a very specific shape. So for example, if k was divisible by 7, then this fundamental domain was essentially two-dimensional. There were only just a few of these elements outside of this two-dimensional part. And as k grows, only this two-dimensional part actually grows. Okay, since I'm talking about automated conjecturing, I will not talk more about the proof, but rather let me say that one can use this system to easily generate other conjectures simply by changing the input data. So you can run literally the same program, but just change the input data. So one of the ideas I had is that I mentioned that there are Frobenius, so there are formulas for Frobenius numbers of arithmetic sequences and for geometric sequences. So I was wondering whether it's possible to generalize this. So the most natural generalization is probably to use the first order linear recurrences. And for one of them, where each term is given as 3 times the preceding term plus 2, I have managed to create the following conjectures. So the formula depends on whether x is 1 or 3 modulo 4. Of course, x cannot be even here, because then all the 4 numbers would be even, and this probably makes sense only if the starting quadruple is relatively prime. Okay, these are the conjectures we have managed to get with this grammatical evolution. And even the size of the tuple is easily changed. So for the 6 tuples of the following shape given here, so these are essentially like 2 arithmetic sequences, and the formula also looks fairly simple. So it's probably possible to prove these conjectures using the same method, the lattice point enumeration method. But other than that, I would like to comment on benefits and limitations of using this grammatical evolution in mathematics. So this grammatical evolution can generate solutions in an arbitrary language by a simple change of the grammar. So grammar is also like one input file in our algorithm, so it's not hard to change it. And this grammar allows us to embed some knowledge in its rules. So for example, we have used the way we create expressions and we have embedded it into the grammar. Or in my case, what I expected is that if there is some division appearing in the formula, then this division would not happen by x or by some expression containing x, but rather by some constants. And I have embedded this into this grammar by not allowing operator to change into division anytime, but rather anytime I use the division sign, I always divide by a constant. Okay, one can also ask, how does this fare compare to a more standard statistical regression methods, or maybe polynomial interpolation methods? Well, it's true that you could have used these methods for this problem as well, and you would probably find these conjectures. So the difference here is that in classical statistical regression, you usually have to give a model. You have to say this is a quadratic function. And the same is for polynomial interpolation. You have to say what is the largest degree of the polynomial appearing. Well, here, you do not have to give the model. You simply give the operators you expect that will appear in the formula. On the other hand, it seems to me like fine-tuning of constants is a potential problem for GE. So this is a stochastic algorithm. So if you run my code, you will not always get the same result. And I think that one of the reasons is that this tuning of constants can take a lot of time. Compared to that, the classical statistical regression works better. But I would like to convince you a bit more about how general this is. So one more possible application and where geometrical evolution was really used is the problem called Santa Fe Ant Trail. So this is a toroidal grid. So you can look at this square, which is 32 times 32 square grid, and you can wrap it into a torus. And the problem here, and there is some food on this grid, and the problem here is to navigate an artificial ant to pick up all the food on this grid. And this ant has only, essentially only 4 commands. So it can turn left, it can turn right, it can move ahead, so 1 unit square ahead, or it can check whether there is food in the direction he's facing. And the grammar that was used to solve this type of problem looks like this. So this grammatical evolution essentially allows you to write an algorithm, to write a program that will write a program to solve your problem. Of course, as I've said before, this was started by Chomsky in describing the English language. So if context-free grammars are capable of describing the syntax of the English language, then they certainly can describe a lot of different problems as well. Okay, and maybe this is a list of references, but maybe on the first slide, these are like the 2 most important references. Okay, thank you.
Thank you very much. Nikola?
Yeah, I'm here.
I would ask you if anybody has some questions to the presenter, please. You can make the questions both on the chat or open the microphone. I think there is no questions by the moment. We'll again express our gratitude to Nikola for presenting his work here, and I will prepare the transmission for the next presentation in this while. Thank you very much, Nikola.
Thank you.